Hey there guys, the AlphaKoala here, just doing a video response to a question I received earlier today. Okay, so the question says that you had a car traveling around a bent curve that was designed for a car traveling at a different speed. So your car is going slower than it should be. So to keep it on the road, what coefficient of friction is required? Okay, now, the first thing you're going to have to do is work out what the road was designed for. So you can use that, go AC equals V squared on R, that's centripetal acceleration equals V squared on R. You can just put your values in, your design values, so it's designed for a 100 kilometer car, you put 100 in, and if the radius was, 50, then 50. Okay, and you can determine that. We know that F equals ma. So we've got acceleration, so we just need to times it by mass. We don't know what the mass is, it's got to hold for every car, so we can just leave m there. So then the centripetal force will equal mac. So that's just mass times acceleration, and that will all be in newtons. Okay, but that's not the only force acting on the car. You've also got gravity, because gravity's got to be going down, and, unless you want your car falling through the earth, you're going to have to counter that somehow. And that's what we're going to do. We're going to create a force to counter gravity, which will be 9.81 m, 9.81 times mass, and we're going to need a force of this, and that's just going to be m times AC, right? And this force was created by banking the road, and what does banking the road do? Well, that just changes the direction of your normal force. So this is going to be your force normal. But what we're interested in is this angle in here. So we know that your normal force is going to be acting at this angle to the horizontal, because this was a horizontal component, and this was a vertical component. So we know that your normal force will be acting at this distance. Then we go to our regular car, which is going to be AC equals V squared on R again, but, its velocity is different because, it wasn't designed for this. Okay, so we can do the same thing, F equals ma, now we AC1, and so the centripetal force of the actual car will equal, AC1m. I should put m on the other side to be consistent, but that's not an issue. Okay, so we know the value of that. We know it's still going to have to be pushing up 9.81 up as the second car we're flying out. So your second car essentially wants to have a force acting up on it of 9.81 times mass to counter gravity, but it only wants a force of AC1. Oh, we'll say NAC1. So mass times the centripetal acceleration. Alright. So you can calculate this angle in here as, say, I don't know, that. Don't know what the name for that is, I should. Okay, so these angles will be different. Why? Because it was designed for this, but the car is actually doing this. So this is being forced on the car, because this is a resultant of gravity and the curve of the road. So currently your car is experiencing this, but it only wants to be experiencing that. So we need to add something. We need a vector to kind of, add to this to create this, and that is going to be your friction vector. Okay, so I'm just going to rub out all this working, but I'll leave the diagrams there. Okay. So you've got this force being put onto your car, and that's going to be fear from the horizontal. That's the force that's being put on the car, but you only want to be experiencing, this much force. And that's going to be alpha from the horizontal. That's going to be feeder in there, right? This whole big one is going to be this, and we're going to call this angle in here beta. And beta is just going to equal this take feeder, so beta equals that take subtract feeder. So you can work out what beta is by that. Okay, now we know that that is the normal force. That is created by gravity on the road, and, that's not going to change per car. So that's your normal force. We know that friction acts perpendicular to your normal force, so we can say that this angle in here is 90 degrees, right? Now, at no point so far have I actually calculated the hypotenuse of anything, and that's because it doesn't really matter too much, and you really shouldn't be doing it. Okay, so this all kind of looks a bit confusing, but we got a force, normal here, which we got from over there, and its angle. We got a frictional force here, which we are adding to the normal force, to create the required force here. So we'll call that force, required, or force resultant if you want. Okay, now we know that mu, the coefficient of friction, equals the frictional force over the normal force. Okay? We also know that tan feeder equals opposite over adjacent. Right? So if we look at this, we've kind of got an angle in here, so we can even say, to simplify it a bit, we'll say tan beta. That's just any angle in there. So tan beta will equal the opposite, which is force, frictional force, over adjacent, the adjacent to the angle, which will be the normal force. So in fact, tan beta will equal mu, because these two are equal. So you could say that, mu equals force over Fn, which is equal to tan beta. Because that's just going to be your opposite, and that's going to be your adjacent. This part here is kind of a shortcut. If you wanted to, you could say, I know this value, because you could calculate it from over here, so I can, work at this and this. The reason we had to use this value here, and just substitute it straight in there, is because this has got a horizontal, this has got a vertical component of 9.81, right? We know that this line here has a vertical component of 9.81. So, if frictional force is acting up at an angle, which it will have to be because that will be your plane there, so frictional force will have to be acting that way. If this had a vertical distance of 9.81 and you added friction to it going up that way, you'd have more of a 9.81 here. So in fact, this normal force will not be equal to this normal force. They'll be going in the same direction, which is perpendicular to the plane. So that's just 90 degrees in there. They will be going in the same direction because the slope hasn't changed, but their values will be different. And, you know, that's okay. They shouldn't be they shouldn't be different too much, but that's fine. That's just why we haven't kind of used this value for this. But now we have angle beta. We have, well, with angle beta, we can just use tan beta equals frictional force over normal force, and that would give us mu. So if you put tan beta in, you'll instantly get your answer. But if you kind of want the longer kind of route, which is fine, because life's a journey, it's not about the destination, you could say, well, I know that the force it wants, the resultant force, will be equal to this. And that's true, because it's going to want to have a total of 9.81 in the vertical, and a total of NAC1 in the horizontal. So you can say, you know, Pythagoras, find that value out as FR, put that in there, and then go, well, frictional force will equal this value, and that would be this direction. Frictional force will equal that value, normal force will equal that value, plug it into that, and you'll get mu. Hopefully that kind of explains. It's a little unclear, it's a pretty difficult question. Basically all I've done is calculated the normal force on each car, because every car will be experiencing the same normal force. That's what the road was designed to input onto the car. I worked out the required force to keep the car going at a lesser speed or a greater speed. I then found the differences in the angle, and then I just said mu equals frictional force over force Newton, which is opposite side over adjacent side, which is going to be equal to 10 beta. Okay, so hopefully everyone got that. Okay, and that is all. Out for out.